In this lecture, we show the standard result that the value of the winding number of a closed contour around a complex number is always an integer. Let the contour C be given by the continuous parameterization z equals z of t, where t is on the closed interval from alpha to beta with alpha less than beta. C being a closed contour means that z of alpha equals z of beta. Because C is the image of the compact interval from alpha to beta under the continuous map z equals z of t, C is also compact. And so, if z sub 0 is not on C, there is a positive real number d such that the smallest distance of z sub 0 to any z lying on C equals d. Let the interval from alpha to beta be partitioned by the increasing sequence alpha, which we set equal to t sub 0, t sub 1, t sub 2, etc., 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 all the way up to t sub n, which we set equal to beta. We will assume that z prime of t is continuous on each t sub interval from t sub k minus 1 to t sub k for k equal to 1 to n. We should point out that z prime being continuous on each closed interval from t sub k minus 1 to t sub k does not mean that z prime exists at an endpoint t sub k, because the left-hand and the right-hand derivatives of z at t sub k may not agree. Still, because of the continuity of z prime on each t sub k subinterval, there should exist a positive real number b such that b is greater than the absolute value of z prime. And when we say z prime, this includes the left-hand and the right-hand derivatives of z for all values of t on the interval from alpha to beta. The winding number of C around z sub 0 equals 1 over 2 pi I times the contour integral along C of dz over z minus z sub 0. With the conditions we have imposed on C and its parameterization, the winding number of C around z sub 0 as an integral converges or is finite. The winding number of C around z sub 0 is also continuous when regarded as a function of z sub 0. One can refer to the video, The Winding Number Introduction, for the proofs of these properties of the winding number. We have included a link to the video, The Winding Number Introduction, in the description of this lecture. The main theorem that we will prove in this lecture is the standard result that if z sub 0 does not lie on C, then the winding number of C around z sub 0 is always an integer. To get started with the proof of this theorem, we define the function phi, where phi of r equals the integral from alpha to r of z prime of u du over the quantity z of u minus z sub 0 plus some constant k for every r on the closed interval from alpha to beta. Since z sub 0 is not on C, z of alpha minus z sub 0 is not equal to 0, so that z of alpha minus z sub 0 has at least one complex logarithm. Recall that every non-zero complex number w has infinitely many logarithms because every logarithm of w can be written as the natural logarithm of the absolute value of w plus I times the principal argument of w plus an integer multiple of 2 pi. We define phi of alpha to be one of the many logarithms of z of alpha minus z sub 0. Phi of alpha will not be a specific logarithm of z of alpha minus z sub 0, but any logarithm of z of alpha minus z sub 0 will do. With phi of alpha being equal to one of the logarithms of z of alpha minus z sub 0, e raised to the power of phi of alpha should equal z of alpha minus z sub 0. We set k equal to phi of alpha so that phi of r equals this quantity. By using virtually the same argument to show that the winding number is finite, one can show that phi of r is also a finite complex number. We leave this as an exercise for the viewer. We claim that phi is continuous for every r between alpha and beta. To prove this claim, we first suppose that r is neither alpha nor beta. We choose a non-zero delta that is small enough in absolute value such that r plus delta is strictly between alpha and beta. Then, using the definition of phi, the absolute value of the difference between phi of r plus delta and phi of r equals this quantity. K cancels out. Then we combine the integrals so that the integral goes from r to r plus delta. Then we take the absolute value of the integrand. So the absolute value of the difference between phi of r plus delta and phi of r this time is less than or equal to the absolute value of the integral from r to r plus delta of the absolute value of z prime du over the absolute value of z of u minus z sub 0. We have retained the outer absolute value because r plus delta can be less than r since we have not specified the sign of delta. The absolute value of z prime is less than b. And since the minimum distance of z sub 0 to any z on the contour C is d, the absolute value of z of u minus z sub 0 is greater than or equal to d. Therefore, integrating from r to r plus delta, the absolute value of the difference between phi of r plus delta and phi of r should be less than or equal to b over d times the length of the interval of integration, which is not delta, but rather the absolute value of delta. b over d times the absolute value of delta tends to 0 as delta tends to 0, so that phi of r plus delta minus phi of r tends to 0 as delta tends to 0. Now, if r were to be equal to alpha, we would have the difference phi of alpha plus delta minus phi of alpha, with delta approaching 0 from the right, or along positive values. And if instead r were to be equal to beta, we would have the difference phi of beta minus phi of beta, with delta still approaching 0 along positive values. Beta minus delta, of course, will approach beta from the left. By using a similar argument to the one that led to this inequality, we can show that both these absolute values will be bounded for delta greater than 0 by b times delta over d, which tends to 0 as delta tends to 0 from the right. Therefore, since phi of r plus delta minus phi of r tends to 0 for all values of r on the interval from alpha to beta, and coupled with the fact that phi of r is finite, phi is continuous for all values of r. To continue with the proof of the theorem, we define a new function h where h of r equals the quantity z of r minus z sub 0 times e raised to the power minus phi of r for every r between alpha and beta. Since phi is continuous, h is also continuous on the interval from alpha to beta. H prime of r equals z prime of r times e raised to the power minus phi of r minus the quantity z of r minus z sub 0 times e raised to the power minus phi of r times phi prime of r. By the definition of phi and by the fundamental theorem of calculus, phi prime of r equals z prime of r over the quantity z of r minus z sub 0. We can cancel out z of r minus z sub 0 since it is never 0. And so h prime of r equals 0. Therefore, h of r, like a step function, must be equal to a constant c sub k on each t subinterval from t sub k minus 1 to t sub k for all k from 1 to n. And since h is continuous, these c sub k's must be all equal, so that h is constant over the entire interval from alpha to beta. Furthermore, h of r should equal h of alpha, so that the quantity z of r minus z sub 0 times e raised to the power minus phi of r equals the quantity z of alpha minus z sub 0 times e raised to the power minus phi of alpha. This is true for all r, including beta. Since C is closed, z of beta equals z of alpha. Since z of alpha minus z sub 0 is non-zero, e raised to the power minus phi of beta equals e raised to the power minus phi of alpha. Or equivalently, e raised to the power phi of beta equals e raised to the power phi of alpha, so that phi of beta and phi of alpha are logarithms of the same complex number. And being logarithms of the same complex number, phi of beta and phi of alpha must differ by an integer multiple of 2 pi I, or that phi of beta minus phi of alpha equals 2m pi times I for some integer m. By the definition of phi of beta minus phi of alpha equals this integral. We divide by 2 pi times I to get the winding number of C around z sub 0, and the winding number of C around z sub 0 equals m. Therefore, the winding number of C around z sub 0 is an integer. Since the winding number is a continuous function of z sub 0, the winding number has the same integer value for points in the interior of C and assumes another integer value for points in the exterior of C. We apply this result to determine the winding number of C around z sub 0 for z sub 0 in the exterior of C. Let D be the interior region of C. We make the claim that if z sub 0 is in the exterior of C so that z sub 0 does not belong to the closure of C or the union of C and D, then the winding number of C around z sub 0 by the integral formula of the winding number equals 0. The absolute value of the winding number of C around z sub 0 is less than or equal to 1/2 pi times the integral of the absolute value of z prime of t dt over the absolute value of the quantity z of t minus z sub 0. Z prime is bounded by B on C. The absolute value of z of t minus z sub 0 is greater than or equal to d. Integrating from alpha to beta, we find that the absolute value of the winding number is less than or equal to b times beta minus alpha over d. We let z sub 0 tend to infinity so that d tends to infinity and b times beta minus alpha over d tends to 0 so that the winding number of C around z sub 0 in the exterior of C can be arbitrarily small. Therefore, since the winding number is constant and is an integer in the exterior of C, the winding number of C around z sub 0 must be 0 for z sub 0 in the exterior of C.